Last time we taught a model to write, feed it a seed, crank the temperature, and it dreams up the next word, then the next, in one single language. Today we make it bilingual. Translation isn't generating from nothing, it's mapping between two languages. You hand it English, it hands you back Spanish. We're still parked at the build stage of our pipeline, but the network gets a second half. This is the encoder decoder, the shape the original transformer was born in. Let's build a real translator. Here's the core idea. Generation had one stack of layers reading and writing the same stream. Translation splits that in two. One stack, the encoder, reads the whole English sentence and digests it. A second stack, the decoder, writes the Spanish, leaning on what the encoder understood. Two jobs, two stacks, one bridge between them. The encoder's only job is comprehension. It takes I love machine learning, looks at every word at once, and with self-attention it lets each word soak up context from all the others. Machine and learning fuse into one idea. What comes out the top isn't text. It's a context-rich numerical summary of the English, a meaning frozen into vectors. Then the decoder writes, left to right, one Spanish token at a time. It starts with a single start token, predicts me, feeds that back in, predicts Encanta, feeds that back in. Same autoregressive loop you saw in text generation, but now it's not improvising, it's translating something specific. And here's the bridge, the piece that makes it translation and not just guessing, cross attention. Every time the decoder is about to write a Spanish word, it reaches back and looks at the encoder's English summary. What part of the source matters right now? Self-attention looks within a sentence. Cross-attention looks across, from Spanish back into English. Watch what that buys us. When the decoder is about to write aprendizaje, cross-attention lights up over learning on the English side. When it writes gato, it's staring straight at cart. Nobody told it. Those words mean the same thing. It learned the alignment from thousands of sentence pairs. The magenta arrows you'll see in the figure are exactly this, the bridge wiring each Spanish word back to the English it leaned on. But the decoder has to play fair. While it's learning to predict word 3, the real answer for word 3 is sitting right there in the training data. We can't let it peek. So we slap a causal mask on the decoder's self-attention. Each position can't see the words before it, never the words after. It has to earn every prediction from the left, exactly the way it'll have to at inference time when the future genuinely doesn't exist yet. Last concept, how do we know it's any good? We use BLUE. It compares the model's Spanish against a human reference translation and measures how much the engrams overlap. 1 is a perfect match, 0 is gibberish. For a tiny model trained on a small dataset, anything north of 0.3 is a genuinely usable translator. Keep that number in your back pocket. And here's the catch that sets up everything next. We trained this translator from scratch. Every weight started as noise. That's enormous. It has to learn English, learn Spanish, and learn to map between them all at once from a few thousand sentences. Next episode, we stop paying that tax. We borrow a brain that already understands language, a pre-trained transformer called BERT, and just fine-tune the last bit. Let's look at the code. 4 short pages. Page 1 preps the data and, this matters, protects our start and end markers from being scrubbed away. Page 2 is the heart. The positional embedding, the encoder block, and the decoder block with both kinds of attention. Page 3 wires them into one model and trains it. Page 4 writes the greedy decode loop and scores BLAU. Everything you need for a working translator, top to bottom. Imports and the data. We load English-Spanish pairs and wrap each Spanish target in start and end tokens. The bookends the decoder uses to know when to begin and when to stop. Now a trap. Text vectorization by default lower cases and strips punctuation. which would tear the brackets right off our markers. So for Spanish, we hand it a custom standardizer that lowercases but leaves start and end intact. Two separate vectorizers, English and Spanish, don't share a dictionary, each adapted to its own vocabulary. Positional embedding. Attention is order blind on its own. Shuffle the words and it can't tell. So we add a token embedding and a position signal, so dog bites man and man bites dog come out different. Mask 0 true on the token embedding tells every later attention layer to ignore the padding automatically. We use this same layer for both the English input and the Spanish input. The encoder block, one multi-head attention doing self-attention over the English. Note kdim is the model width split across the 8 heads. A feed-forward network and 2 residual plus layer norm wrappers. No causal mask here. The encoder is allowed to see the whole sentence at once. That's the entire comprehension engine. The decoder block, and this is where it earns its keep. First, self-attention over the Spanish written so far, with use causal mask true, the line that forbids speaking ahead. Second, a cross-attention multi-head attention. Its query is the Spanish, its key and value are the encoder's English output. That's the bridge. Then the feed-forward net, 3 sub-layers, each residual normed. Now we assemble the full model with the functional API. 2 inputs, English source and the shifted Spanish target. Source flows through positional embedding into the encoder. Target flows through its positional embedding into the decoder, which also receives the encoder output for cross-attention. A dropout, then a final dents over the Spanish vocabulary gives a score for every possible next word. Compile and fit. Adam, sparse categorical cross-entropy. Sparse because our targets are integer token IDs, not one hots, and from logits are true because that last dents has no softmax, and accuracy as a quick readout. We fit for 30 epochs. You can watch validation accuracy climb as it learns the alignment. The payoff, translate, vectorize the English once, seed the Spanish with start, then loop with a real step counter, predict the next token at position I, take the argmax, that's greedy decoding, append it, and feed the growing sentence back in. Stop when the model emits end, or we hit the length cap, map the IDs back to words, strip the markers, and you've got Spanish. And the scoreboard. We translate a held out set, run blue against the references, and print a couple of live examples. I love machine learning comes back, me encanta el aprendizaje automático. Blue lands around 0.34, a real working translator, built from 2 attention stacks and a bridge. But every weight here was learned from scratch, English, Spanish and the map between them, all from 9,000 pairs. Next time we stop starting from 0, we fine-tune BERT, a transformer that already speaks the language, and watch how little data it takes. See you there.